Well, I think we're going to go ahead and jump into it here. If others join later, they can catch up. What I was going to do is, since I kind of left you hanging a bit with the example on Thursday, I was going to wrap that up as the starting point for today and just remind you where we were on that session. So I did an example and made some errors in the code, which I subsequently corrected when trying to do this, just the binomial base model here that was sort of the first example. Let me quickly just show you what we got there when we actually correct the code on it. Let's actually got a session open already. As I posted, well, indicated on the website, I had posted the corrected R script and model. Actually, there was no corrections to the model. It was as before. Corrected the R script, and it turned out one of the errors was just a very trivial one where somehow I had managed to create a file called hands1 on base here. So when the program tried to create a new directory, it just had a problem with that. The other problem was just making far too complicated a graphics function based upon a template that really wasn't a suitable fit. So here I ended up doing a simpler one, and here I'll just show you the sort of the basic results here that we get from this example. Fire it up. Recall that if we take a look at our model here, it was a very simple logistic linear regression. So we've got two parameters to deal with, our theta 1 and theta 2, or intercept and slope, in our logistic regression model. And when we look at our history plots, we see we get our nice fuzzy caterpillars here with the number of iterations we use, so no apparent convergence or mixing problems there, so seem to be okay with that. And this just gives you a visualization then of the marginal distributions for our theta 1 and theta 2 in here, and you can kind of get some idea of the values. That we've got something that's centered in our intercept here, what is that, around minus 0.4 thereabouts, and we have our slope that's centered, looks like it's somewhere around minus 0.015 or thereabouts, and it's pretty clear that it's pretty well separated from zero in this instance. This is just the Gelman-Rubin-Brooks plot, and again we're looking for these to be close to 1, and they do end up getting close to 1 as we get out towards the end. And finally, this is the plot that I made far more difficult than necessary before, and what we're looking at here then is taking our fraction of patients with pulmonary exacerbations, plotting them versus dose. And of course, we're hoping for a drug that would bring the incidence of those down, and the incidence does appear to go down with dose, and the model predictions are also quite consistent with it. And you can see plotted against the observed data, we've got a posterior median and a 90% credible interval about that, just as a way of depicting our model fit in this instance. So that's our basic base model here, but only suitable for making inferences about the effect of dose. And then the additional aspect of the exercise was then to take it a step further and go on to what I had termed the binary full model, which is now, in this case, we're going to want to take some individual specific covariates, some of them being continuous, and so in this case it's more difficult to break out the model in terms of subgroups where we can use a binomial model. So we're going to be working with our individual binary data in this case. So first of all, the core model here, our data now, instead of being the number of patients in the ith group, it's going to be the ith patient. and we're going to have values now expressed as zeros or ones, 0 for no exacerbation, 1 for the occurrence of an exacerbation. That's going to be described in terms of a Bernoulli distribution with a single parameter representing the probability of having greater than or equal to 1 exacerbation over the period of the trial. And then we're going to explore the influence of not only dose, but the covariates of our baseline FEV1, whether or not the patient is taking chronic antibiotics or chronic DNase, as well as patient age in this case. So we'll do it as a straight binary. For all the thetas here, I'm going to throw a pretty flat prior here at that. And let's go take a look at what this time I'm not going to do it, try to program it in real time here. We'll just do a brief run through of the solved problem here. Okay, let's get rid of this. Okay, and I've actually opened these up already. And here we've got the model itself is being expressed. So again, everything's inside of a model block. And then we have a group of observations. So we've got I from 1 to number of observations, or in this case, number of observations is equivalent to the number of patients in here. The exact is our data item, which takes on a value of 0 or 1 for each patient. And so here we've got the WinBUGS equivalent of our likelihood function that we expressed in the previous slide. Then we've got our linear model for the logit transformation of that probability, our p-exact. And again, that's just the WinBUGS equivalent of the expression we just looked at. So we get that theta 1 plus theta 2 times dose, and you can see we've got our subscript I on dose, theta 3 times our baseline FEV1 minus 70. So we just tried to center that around somewhere near the average. Theta 4 times antibio. Antibio is an item in our data for indicating it's a 0 indicating no antibiotic, or 1 indicating chronic antibiotic use. A similar kind of variable for DNase use. And then finally a centered age here. So we've got age minus 18 in here. So that's really in total represents the likelihood function for our model. And then for the, scrolling too fast, there we go. For prior distributions, I just took advantage of using a for loop as a shorthand here, just to assign, again, a fairly flat prior here, in this case normal, with a variance of 1,000,000. And that coupled with the likelihood is really all we need to get the posterior distribution of our parameters. And again, if we want to get a posterior prediction of observed values, we can do that in here using a statement like this, which again is just like, scroll up here, which is just like the likelihood statement, except on the left-hand side we have a new variable which does not exist in the data set. So we're actually going to be predicting then values for exact. So it's just going to generate a bunch of zeros and ones given the model predicted values for the probability of exacerbation. Let's see, just realize in case you have, no, okay. Okay, so that's the model we're going to be using. The R script that corresponds to that, come on, there we go, has a structure very similar to the one we went through on Thursday. So the core structure is pretty much the same. The main specifics that are going to change is when we put the data set together to pass it in and then do the plots at the end. Those are going to be more specific to this particular case. So most of the stuff in the beginning, again, is just a matter of putting in the correct name for our model. Then we get a certain amount of boilerplate. We read in the data set. Whoops, grab the wrong thing there. read in the data set here, just as we did before. In fact, it's the same data set. The difference is this translates even more simply to the data set we're going to want. I'm going to skip over these exploratory plots here. You can explore those if you want later on. I want to go down to where the data set is created. In this case, we don't have to sum things up because we're not creating the samples suitable for a binomial. We're just going to leave them binary, and we're basically all we need then. Sorry, I scrolled too far. There we go. So for the bugs data, we can component here. That's going to be pretty easily constructed from the data set. So our NOBs, or number of observations, again equivalent to number of patients, is just equivalent to the number of rows in our data set. And then we basically just grab the columns from our data set. So we've got dose is the dose column, FEV1 baseline is the FEV1 baseline column, and so on, right down the row here. We just grab the appropriate columns and pass them in into bugs in here. For bugs in it, as before, right now, all the parameters we have to provide initial estimates of are the six thetas, which is provided here as a vector, where I'm just going to generate different values for each chain using a normal distribution, and I actually did an initial fit, which is shown, let's see, in this previous line. Scroll back. In fact, let me put a line break in that so you can see what's going on. What I've done is use the GLM function here to fit a generalized linear function, in this case a linear logistic regression function, using one of the built-in R modeling tools here, and I'm going to use the values from that as my initial estimates, or at least for centering the initial estimates around that. So that's why you can see this thing calling the coefficients then of that GLM fit, which again in this case is just going to give me those 6 different parameters, and I've ordered them in the same order that I wanted, that I've got them included in the original data. So that works. I'll be honest, I don't remember where I dreamed up the 0.6. I'd have to go back and look. I think I just picked up something rough on that. Alternatively, you could actually get standard errors out of the GLM fit in that and use the standard errors for those coefficients. What I'd probably do is actually put a number here that's a multiple of those standard errors, just so that you get a sort of over disperse set of initial estimates here, so it's a better test of your convergence. Okay, let me just check something. No, okay. Oops. Okay, so that's really the core there. We also have to tell it what parameters we want to save, and the main ones, of course, are going to be our thetas, and then we're going to want to get things like our model predicted probability of exacerbation, and then the model predicted exacerbation occurrences. So we're going to keep those. Then again, the bugs call itself is pretty much boilerplate, except for making decisions about things like number of chains and number of iterations in here. Again, I often use numbers similar to the ones you see here for a lot of problems as a first attempt, but then look at the results to see whether that's actually adequate for the problem. And let's see, again, we got some boilerplate after that for reorganizing the data, opening a PDF device for collecting our plots, getting a summary table in here, and then where things start getting model specific again is when we get down into this section labeled posterior predictive distributions. And these are somewhat similar to what we looked at before, except it gets a little more complicated by doing things like calculating things like fractions, fractions of patients with exacerbations, but for different subsets of patients, and plotting those results. And I'll show you those in a minute. I wasn't planning on going through the individual plot descriptions here. Oops. But I encourage you to go ahead and take a look through them. And if you hit sections of the code that you're curious about but puzzled about, feel free to either email me or post something on the forum. I would say probably post it on the forum so that others can have the advantage of seeing the interchange. And let's see. I think that's about the only story I wanted to tell on the R script. And then I was going to show you the results. Let's go back to there. Let's see. These are, yeah, I ran this before. So let me go ahead and just grab these. Actually, even before I do that, let's go ahead and open the summary table here. Oh, it's probably hiding behind again. Yep. Okay, so we can see this here. So we can get, as usual, we get a deviance in here. And just a reminder, deviance here is minus 2 times of the log of the likelihood. Again, in a Bayesian framework, that thing actually has a posterior distribution. And so you get that summarized here, and that can be useful for model comparison. And then we've got our 6 thetas, our model parameters in here. We've got our posterior means, posterior standard deviations, again our naive standard error and our time series standard error. So one of the initial diagnostics I'm going to look at will be to look at like the time series standard error as compared to the posterior mean estimates here. What I'm hoping for is that these time series standard errors are relatively small compared to my posterior mean, and in this case I'd say that overall that's true. The other thing that's a related measure is to take a look at effective n, and I'm looking for a number here ideally in the thousands or at least the high hundreds, and here we've clearly well into the thousands. In fact, as I recall when we did this calculation, there are 3,600 retained samples. So technically this number shouldn't even be bigger than 3,600. That sometimes the technique used to estimate it will come up with a bigger one, and we actually do have one that says 3,800. But in either case, you can see these numbers are large, on the same order of magnitude as that 3,600, which is saying that there's very little autocorrelation on our MCMC samples, and certainly enough for good precision. And then we get our various posterior quantiles here. So you can certainly explore over that and use it to answer questions like, does age appear to influence the results, and in the other covariates, the use of our DNase and the use of antibiotics. And some of these, so you got the influence of dose, which is the first one, and clearly that's pretty well separated. Actually, we actually have one. There's actually a crossover on 0. I'm sorry, that's theta 1. That's not the one I want. Here we go. Here, that's the next one down here, which is dose, which clearly has an effect if we go by that. The next one I believe was, which one? Now I'm forgetting the order. Easy enough to check. Let's see. There it is. So we got theta 2 is dose, theta 3 was FEV1, theta 4 antibiotic, 5 DNase. Okay, we bounce back to that. And I see there's a question. I'll come back to that in a moment. So again, we've got what? That's FEV1. I gotta remember again. FEV1, yeah, antibiotic. DNA, I'm sorry, age is there. That's got to be DNase. That's got to be antibiotic use. let's see, that one would be FEV1. So there's maybe a little bit of ambiguity in the case of our two drugs. There's certainly a fairly strong trend in there. So you can make some inferences based on that. Let's see, I saw there was a question that popped up. What was it here? I was asking about is time series standard error preferred rather than naive standard error? For really making inferences about the uncertainty in your estimate of the posterior distribution. So these MCMC samples in the limit should look just like samples from the posterior, but how much accuracy you have in estimating characteristics of that posterior depends upon things like that time series standard error or the effective N, and so the naive standard error, on the other hand, makes no adjustment for the autocorrelation in the MCMC samples. So with some models where there's a lot of autocorrelation, the naive standard error could be quite misleading, because you could easily have a situation where the true uncertainty in the posterior mean is much greater than what the naive standard error would imply. Roughly speaking, what you would expect to be true when you look at the relationship among the naive standard error, the time series standard error, and this effective N is that let's say, make sure I get this right. Well, first of all, the naive standard error is really just the standard deviation here divided by the square root of the number of MCMC samples. So assuming I've got that right, this number here should equal 3.44 divided by the square root of 3080, if I've done that correct. Whereas I'm sorry, I said that wrong. No, sorry, it would be 3.44 divided by the square root of 3600, the number of samples we ran, whereas the time series standard error will be approximately equal to the standard deviation divided by the square root of the effective N in here. It isn't quite an exact relationship in this, because the programs that estimate the time series standard error and the effective N actually use different algorithms for calculating those two. So there's sort of two different algorithms to go at roughly the same thing. So they don't come out exactly what I said, but that's approximately what would be true. Let's see, anything else there? No. Okay. And I wanted to show you the plots. Fire those up. Too many of them here, but we'll try and weed through them. Okay, is it finished opening them? Okay, let's go to, we're actually looking, I think, we're looking at the first one. So here's our history plots, and you can see we've got nice fuzzy caterpillars here. Everything's very well mixed. So this is consistent with those high effective N's and low values of the time series standard error that's consistent with the kind of precision we got. So that's a good thing. In other words, we've actually got more than enough samples. Let's go to actually, I didn't want the base plots. Where is number 2? There it is. Oh, that's just the last of the thetas. Okay, we can get rid of that. Okay, number 3 is probably, okay, there we go. So there's our marginal posteriors on these, and again, you can look at these in terms of the kinds of inferences we might be interested in terms of, we got our intercept, our slope relative to dose. So again, clearly that's reasonably well separated from 0. And I'm always going to forget the order. I think 3 was the baseline FEV1, again pretty well separated from 0. Theta 4 was, which one? It was one of the drugs. And you can see that's more or less separated. There's a little more of a tail there. I think that was the antibiotic use, and 5 was the DNA use. And in that case, the DNA, though there's a clear trend, it's not completely convincing, and in fact it actually seems to be in sort of the wrong direction from what we might have anticipated. And then finally theta 6 here, it includes 0 bit there. There's a good chunk of the tail, so again, not convincing evidence that age is playing a strong role in here, though that could be a little bit confounded with the fact that it's highly correlated with the baseline FEV1. Let's knock that off. And let's just look at the basic diagnostics here. Okay, that was again the Gelman-Rubin-Brooks plots, and those are clean as can be in this case. Well, pretty soon we'll have a good example where they're not so clean, so you get some idea what a bad one looks like. Okay, here we finally got some model fitting diagnostics here. So you've got what's been plotted here is the patients have been broken out by whether or not they're on chronic antibiotics. And we're plotting the fraction of patients with pulmonary exacerbations, and you can see the observed value in the dots, and then the posterior predictive intervals and medians for the same subgroup here are shown in the same color as the corresponding dots. So you can see we seem to overall have captured this, so there might be some interesting systematic deviations here that we might explore further if we were doing this in a real modeling problem. So we've captured that. I think I do the same thing in the next plot, looking at the DNA use. Where do we go here? 6. No, this is just the same thing but plotted in a different way. I guess I provided you with some different examples of plots in case you want to explore different ways of plotting these things using R functions. Okay, and let's see what was next. 7. And this is another way to look at it. This is a similar idea. Actually, I'm going to save some of these. These are getting into our discussion later on about posterior predictive checks. So let's not even dig into that right now. I think we've actually probably looked at all we need to for the quick run through, which is what I wanted to do. Yeah, I just flew by the rhDNAs. There's another one showing the plots relative to whether or not patients were on the rhDNAs. Okay, so anyway, that was just intended to be a quick run through to give you some idea of working with that particular example, and can compare your own results too. Let's see. Oh, okay, just a response from Carrie. Okay. So let me take a breath here and see if there's anything you wanted to look any deeper into on that particular example before I move on to a new topic. Okay, nothing popping up yet. I'll keep my eyes open. Let's go on to some new material. And apologies if you've got an earlier version of this. I reordered the presentation a little bit compared to what I thought I'd be doing last week. But even if you do have an earlier copy, you'll still find this in your slide set, but it'll be a few pages forward. I don't remember what the page number was. So I was going to save the discussion about model checking and comparison until next week. Today I was going to talk about doing hierarchical or mixed effects modeling of odd type data, primarily focusing here on binary data. So let's start with a context where it makes sense. So suppose that each patient is treated for 4 weeks and reports whether or not an adverse event occurred during each week. And in fact, this is, let's see, I'm going to remind myself of the example. Okay. So the context here is we're going to look at adverse events, but we're not just going to look at whether or not an adverse event occurred in a patient over the entire study. We're going to break it up into segments. So we're going to look at whether or not an adverse event occurred during each weekly period then over a 4-week study. So in that instance, there would be 4 binary adverse event measurements for each patient. So just as we concern ourselves with in something like population pharmacokinetics, where we want to account for within-patient correlation or equivalently account for interpatient variation, we want to do the same thing when we're working with odd-type data. And in this case, binary data. To do that, we're going to use a mixed effects model that's going to include interpatient variation in one or more of our model parameters. So we're going to talk in terms of patient-specific parameter values. And here I'll just use the symbol, use a lowercase phi to represent that. So I've got phi sub j to represent a model-specific parameter in the jth patient. And we're going to model that according to some parametric probability distribution where the parameters of that distribution, usually the mean, might be functions of patient-specific covariates. And for our example, we're going to assume that our interpatient variation can be described by a normal distribution. So in our case, we're going to be looking at cases where phi sub j would be normally distributed with some mean mu and some variance-covariance matrix here, sigma. So when I'm saying this, theta may be a vector. It's not necessarily a single value. So in this case then, the likelihood for an observation of an individual, our y-obs ij, is the same as we described before in the case where we only had one binary observation per individual. But the difference now is going to be that in pretty much every place where we had put a theta in the previous model, we're going to put this phi sub j. In other words, we're going to be putting patient-specific parameters into our likelihood function. And that's what I'm describing here. So now we're talking about the likelihood in terms of the phi sub j given our observations in the jth individual. So we're talking about the ith observation in the jth individual. And they may have some covariates, in this case dose. And so that's equivalent to our probability density for our y-obs j. And since it's binary, it's just going to be our good old Bernoulli relationship, just like before. So we've got our probability of an adverse event, which will be a function of our patient-specific parameters as well as covariates. And that's going to, you can see that's raised to a 1 or a 0 depending upon whether or not the adverse event occurred. And same thing for the case where for the probability of an adverse event not occurring, raised to the, again raised to 1 minus that 0 or 1 value. And in our case, again, we're going to use our good old linear model as our first example. So the logit of that probability then is some theta. You know what? I should have put phis there. And so consider that a typo. This should have been a phi, and this should have been a phi over here. So that'd be like a phi sub 0j and a phi sub 1j multiplying dose. And the overall likelihood then in our jth patient is going to be to take the 4 values within that patient, and assuming they're independently observed, that we can treat them as independent, then we can just multiply them together to get the individual specific likelihood. So we're almost there, and so we do that. And then finally we have to construct the overall likelihood given all of these individual components. So we've got two things going on. One, we want to combine the individual likelihoods together, and then we want to combine all of those for all of the individuals. So that's the first part of it, is just combining individuals. But then the other side of this is, in many cases, we want our primary inferences not to be about those fees, those individual values. We want them to be about the population values, which we're calling theta. Okay. So to get that, we have to do a little additional work. So the first thing we do is we go ahead and we can write out the joint likelihood for all of these individual specific parameters here. And then we integrate over all of those things. So we have to then concern ourselves with all of these distributions of the individual parameters given the population parameters. So we do that. Well, we already pointed out then that, well, first of all, what you're looking at then is the likelihoods then for all of those individual fees. We're assuming that, let's see, where am I going here? Oh, yeah, we're assuming all the individuals are independent, or their observations are independent of each other. So again, we can just use multiplication of the individual level likelihoods in here. Then we have to take our probability densities for our individual values given the population values, integrate that out. And then finally here I'm just breaking out these individual likelihoods out to the individual observations finally. So we have this mess here to deal with. And if we're working in a maximum likelihood environment, then what we're going to be looking for are the values of these thetas, the population parameters then that maximizes this function. So to do that, we have to deal with the integral. Now classically, the way we've dealt with that in population modeling in pharmacometrics is using NONMEM, which approximates, or NONMEM 6 and before approximate that likelihood using a Laplacian approximation for the integral. And it assumes that all of these p of phi j given theta distributions are normal in there. So that's the approach that was used. With NONMEM 7, there are some additional algorithms available that do not make that type of an approximation. They use iterative strategies that, though computationally more intensive, allow you to get around that type of an approximation. Okay, so there we've described it in the maximum likelihood context. Now we're going to be working with this in a Bayesian context, and we could express it this way, but it turns out that to do the calculations, the most straight ahead way of dealing with this is not to do that integral, but to actually work with the joint posterior distribution of both the individual level and population level parameters in one go. And in effect, what we end up doing is we do the integration later on when we construct the marginal distributions for all of the various parameters. Okay, so now we're going to put this in the Bayesian context. So we're going to take that same example. We've got our adverse events observed over 4 intervals in each patient. And again, as I say, the way we'll work with this is we're going to look at the posterior distribution of both the population and individual parameters in one go by constructing the joint distribution of both of those categories of parameters. So what we want then is this. We want our distribution, our posterior distribution for the thetas and all of our phis in here given our data and our covariates, in this case just dose. And we start writing that out. And as typical in the Bayesian context, we sort of focus on the numerator of our Bayes rule and talk in terms of what is proportional to the posterior distribution. knowing we can always construct a normalization factor to turn that thing back into an appropriate probability density, or distribution in this case. So we've got our likelihood, we've got our distribution of all of our individual parameters conditioned on our population parameters, and finally our prior distribution for our population parameters. In here, the first component of this, our likelihood, is pretty much what we just wrote before. We can break that out across all of our individuals, our 100 patients there. And we've got the other two components in here that we can break out for our prior. Again, this just breaks out the individual observations within each one of those patients in here, and we write the whole thing out. Now, of course, usually we're not programming this in a way we actually have to break out all of these by hand ourselves, but that in effect is what's going on when we structure the model as we're going to within WinBUGS. Okay, so that's basically then describing a population model for binary outcomes in a Bayesian framework. So let's take an example of that then, where we're going to look at mixed effects modeling of some binary data. In this case, it's going to be the meta-analysis of factor 10A, of factor 10A inhibitor's effect on a venous thromboemboli incidence. And I'll just refer to those from here on out as VTEs. And what I've got here are published VTE rates from 7 dose-finding trials comparing new factor 10A inhibitors to enoxaparin. The horizontal lines in here correspond to the enoxaparin result within those studies. In the case of the red line, ignore the dose. That just refers to the fact that in each one of the trials, enoxaparin was given at somewhere in the dose range of 40 to 60 milligrams per day as an active comparator. And then you can see the dose response in terms of the fraction of patients with VTE as a function of dose for each one of these drugs and each one of these studies. So we've got, a YM150 was some, was one candidate out there, rivaroxaban. We've got a couple of studies. We got three different studies there. Pixaban, Lilly candidate here, and rizaxaban, all captured here. So now these have all been reported as fraction of patients with VTEs, but we've also got the total number of patients in each one of those treatment arms. So what we've got is the result of something where the underlying data was binary. It's been reported to us as summary data that we can convert into the number of patients that experience a VTE, and we can treat that then as a binomial outcome. And here's the proposed model to describe that data. It's going to be a linear logistic regression model for VTE occurrence in the ith treatment arm of the jth study. So in this case, our individual, if you like, is not going to be a patient. It's going to be a treatment arm. In other words, so it's going to be a group of patients in effect on this. And so we've got those, and we've got, sorry, I'm actually confusing two issues here. So we've got, it's the we do have, we're only going to have one observation for each treatment arm. So let's see, a treatment arm will function, is going to function more like an observation, and the study is going to be the thing where we have multiple observations. So in this case, instead of modeling inter-patient variation, we're going to be looking at inter-study variation as part of our model. So we still have a hierarchical model, but the individual, if you like, of interest is going to be a study rather than a patient. So we're going to model this as binomial for the number of VTEs in the ith treatment arm of the J study. That's going to be binomial with a probability of VTE which is specific to that treatment arm and study. And then we've got our total number of patients contributing to that treatment arm. We're going to do this as a logistic regression. In this case, it'll be, actually I said linear, didn't I? It's actually not linear. This is nonlinear. It's linear in terms of, well, we will explain in a second. It's linear in terms of one component. But and here I've written the model as the effect, sort of a placebo effect plus a drug effect component in here. The drug effect component is going to be linear with respect to the log of dose plus 1. So I guess in that sense it is a linear logistic regression model. The trick here was to try and capture the fact that there is some degree of nonlinearity that appears to occur in the relationship that we have here. We also have a situation where we want it bounded below by 0 on here. And so that's the reason here is to try and capture an element of that nonlinearity. It also still has the property that when the dose is 0, this term goes to 0, because this becomes because when dose goes to 0, this becomes the log of 1, so you just end up with a 0, and that zeroes out the drug effect when there's no drug present. And then finally, for this placebo component, that's going to be where we have an inter-trial random effect here. So we've got this placebo effect can vary from drug to drug, from study to study. And it's going to be normally distributed about some value theta sub p in here with some variance sigma squared. So that's the model we're going to attempt here. Okay, in this case again I'm just going to use weakly informative priors for the drug effects, but I'm going to use informative priors for the placebo effect. In this case this is a fictional, the prior here is constructed in sort of a fictional way, but I wanted to illustrate the idea of using historical knowledge about control treatment response. And that actually makes some sense in this particular case, because we've reached a point in treatment of VTEs that, or in prevention in this case, prevention of VTEs, so this is actually case where you're preventing VTEs in a post-operative situation. It would be unethical at this point to use placebo for that, because we do have effective treatments for preventing those VTEs. So you wouldn't be able to do a placebo-controlled study now. However, there is some historical data out there that one could draw upon that you could use to construct an informative prior distribution of, and this is illustrating that notion. However, don't quote me on the specific values here. They're strictly imaginative. So the idea here then is we've constructed an informative prior for our theta p, which would sort of be our average placebo effect. So you can see we've got it's normal, and I've centered around a logit of 0.45. And a sort of modest variance term here, and then similarly we've got an informative prior on the interstudy variation. And of course you could in fact construct such a prior from past data if you had previous studies in which placebo was administered under similar circumstances in similar patients. You could use that historical data to construct some informative priors to use those as a historical control. Okay, let's move past that. Let's see what that would look like when you implement that then in WinBUGS. Again, we always start out, everything gets enclosed in the model. So we've got model with open braces, and somewhere at the end there'll be a closed brace corresponding to it. We're going to loop over all of our observations. So this is going to go over all studies and all arms within those studies. So NOBS would be the total number of arms in this case. VTE is going to be data representing the number of patients that experience a VTE. And then again, that's going to be binomial with a parameter representing the probability of a VTE, and the N here will be the total number of patients exposed to the drug in that treatment arm. And then we're going to calculate the probability of our VTE, and we're summing the placebo effect and the drug effect. Drug effect, then recall, was going to be our slope here, our theta, times the log of dose plus 1 in here. And so that's the sort of the core part. What we've described here is basically, I've described this top part here where we've got the binomial component, and then the next two lines is what I've shown you so far. Now I sort of flew by a couple of tricks that are going on inside that, and let's revisit those. Actually, let me visit the trick in a second after I show you another component. Now, one of the issues here is recall that this placebo effect here is something that varies by study, and how do we incorporate that in a WinBUGS context? Now recall in NONMEM we'd introduce these ETAs, and those would somehow be incorporated as part of that. Well, there's a similar notion, but in the way we do this is I create a separate loop. It's outside of this loop going over my observations. I have another loop down here. You can see where I'm looping over all of the studies. So you can see it goes from I in 1 to N study down here, and this is where I model the interstudy variation in our intercept, and you can see it right in this line here. So I've got my my EP, my placebo effect here, then is normally distributed with around some mean that I called EP hat, and some precision tau associated with that. So that's where I generate my study specific values of the placebo effect, my EPs, but then I have to somehow reference that up in the top part of the model here inside this loop. So notice here where I reference the EP value, I include a nested subscript on this. Now what I've done is in the data set I've included an item. You can, if you think of the data set as essentially a square table, what I've done is I've included another column which is a sequence of integers representing the study, and they have to be an unbroken sequence of integers beginning with 1. So they would go from 1 to N study, the number of studies, and that would actually be an item in the data set that we're providing, and I'll show you that in a minute in the R script. So we're going to include that, and so I simply pick out the appropriate one of the values I generated in this other loop by using this nested subscript to pick out that particular the particular value of EP corresponding to that study. So that's the main trick in dealing with the hierarchy here. So to deal with the hierarchy, you have a separate loop for each level of the hierarchy. We've got our interstudy variation in the lower loop. By the way, the order of the loops is unimportant. You could flip these around and it would still work. And then I have the upper loop here, which is looping over all my observations. The other part of this that I didn't mention as we're looking back in here is that, notice here I've got this thing labeled as theta drug. Now that actually what I'm trying to indicate there is that there will be a different theta for each one of the drugs. So recall we had, how many different ones? We had 1, 2, 3, 4, 5 different drugs. So for each one of the drugs there will be a different theta in here. So those are different, so each one will have a different parameter value. So we also have to deal with that. So when I mention these priors down here, this is actually 5 different priors when I say theta drug, but each one shares the same type of prior. Okay, so, and where that crops up is, you can see it right here, where I do that. Notice again I use a nested subscript for a slightly different reason than I did with the interstudy variation. I define my thetas for all the different drugs. I then, for each one of the drugs, I assign them an integer, going from, what in this case, 1 to 5. That'll correspond to my different things. And inside the data set that I pass to WinBUGS, I pass, and again, another column of values that will take that will all be an integer from 1 to 5, corresponding to the different drugs. I guess what you could say one of the downsides to WinBUGS is it only understands numbers. It doesn't understand character strings. So I do have to come up with a code to represent the different drugs. Okay, so that's really the core of the model, and in fact that's pretty much everything we need to do the inferences on that, except for the priors, which I haven't showed you yet. Actually, why don't we jump to the priors and come back to the other stuff. Recall I mentioned that we were going to do informative priors for the placebo response, so that's what this first set of lines is. So here's our EP hat, and what I've used names here so you can see EP hat prior mean, EP hat prior precision. I've assigned values that correspond to the numbers I put in that previous slide, and then I just use those names here. Alternatively, I could have just put those numbers right in inside there. Similarly for log sigma. So basically you've got two distributions correspond to our EP hat and the log of sigma in here. So that's our informative priors on our placebo response, and then our set of uninformative priors for our theta drug values down here. Okay, so that's our priors. Okay, now the other thing that's going on in here that's a little different than when we were working with the non-population case is we've actually got a couple different kinds of posterior predictions. And for those of you that are used to working in a non-mem case, these are pretty directly analogous to what you've commonly termed individual and population predictions. There are, again, predictions very analogous to those in the Bayesian framework. The ones that are essentially equivalent to the individual predictions is what we get with this line right here, where I called it VTE.COND. The COND is supposed to indicate that we're talking about a prediction conditional on the individual specific values of the model parameters. So notice that this looks identical to the likelihood, but again, VTE conditional is not a piece of data, it's a prediction, whereas VTE up here is a piece of data from our data set. And so it's going to generate posterior predictions that are conditioned on this same probability of a VTE that we're generating right here and that is used in the fit. So that one's actually going to be conditioned on our individual specific values of our model parameters, of all of those thetas that we're generating. I'm sorry, it's the individual would be the EPs. Then what's down here in this group of lines down at the bottom of our observation loop is a little bit different. This thing I call VTE pred. Well, the right hand side again looks very similar to our likelihood, except notice I've got a different name here where I have, instead of just p.vte, it's p.vte.pred, and this now is a simulated value of individual predictions. So it's no longer conditioned on the observations for treatment arm I in this case. It's more of a general prediction of that probability, and it's generated from this EP pred value. So what's happening, if you look at this, you'll see that there's a sort of like a chain of evidence. If you go back from the data, you can see, okay, VTE here is connected back through PVTE. PVTE, you can sort of take that chain back to the EP value, and the EP value is generated down here. So this EP value has a fairly direct chain of evidence, if you like, going right from the data here, this VTE, which is the actual individual data. But if you take a look at the chain, if you try to do that for EP pred, or I'm sorry, if you try to do that for this VTE pred, you find the chain back to the original data is a much longer one, if you like. It's connected back to the original data only through the population parameters, not through the individual parameters. As a result, this would be equivalent to predicting the results for new observations in a new study that just happened to have the same design as the one we were fitting to. Okay, so again, let me actually phrase something like that for both of the predictions. What the individual specific prediction you can think of as being a posterior prediction for new observations in the very same study. In other words, we're talking about making what would happen if you took the same patients that were in that particular treatment arm and gave them another dose. What would you predict would happen? Well, in that case, you're going to condition your predictions on the parameters you've predicted for that particular group already, and that will give you individual specific ones. Whereas the population predictions is you're asking a different question. You're asking what would happen if I took a whole new set of subjects, same number of them, gave them the same doses as I did in the original study, but it's a new group of subjects. What would I predict? And that's what these population predictions will be. And of course, just as you see within in something like a non-mem case, is that the distributions of these are different. The individual specific predictions are generally going to fit closer to the observed data for each individual, and the prediction intervals will be narrower than they are for the population predictions. Okay, let's see. Is there more I wanted to do on this before jumping? Oh, okay, there we go. Sorry, it's moving very slow all of a sudden. Okay. Debating on how far to take this. We've actually sort of run out of time here. I guess what I'm debating on doing here is I don't want to give too short a shrift to actually stepping through this and going through the results on this. Maybe what I'll do is let me give a quick run through the results here, but actually start in the middle and spend a little more time on them next time. And this is actually going to lead to an assignment here. So let me get at least to the a brief description of the assignment. So anyway, this was one where we ran it. You can see the model fit in this case, or you can see the history plots, and they're fairly clean. You can see the model fits in this case. Notice you can see the distinction here between the predictions of new data in the same studies, in other words, our sort of individual study predictions, versus these where we're predicting new data and new studies of the same design, in other words, sort of population predictions in this case. And you can see some of the distinctions there, and in general the model seems to do a moderately good job of describing the data, albeit pretty noisy data. You can look over the parameter estimates here and see if they make any sense to you. And let's go ahead and let me give you just a brief run through on what I want you to do for hands-on problem 2. And what we'll do on Thursday is I'll do maybe a little bit more about the example I just did, but we'll spend more time on the results for hands-on problem 2, which has a lot of similarities to, let me actually remind myself what I'm getting you into. Actually, I'm getting you into a lot. You know what? I'm going to change this because I gave some extra complications in hands-on 2. Let's actually make it a different assignment for this week. We've got enough weeks. I think we can afford to do that. for this Thursday, I'd actually like you to dig into the details of the example that I've given here and run it for yourself. If you really want to challenge yourself, pretend like you didn't see the WinBUGS implementation here, and you could go ahead and do it. Let me point you to where this is in the distribution you've got. This one is what's right here. This folder here called Binomial ME example. That's supposed to stand for binomial mixed effects example. That's the one I've just been talking about. So, it depends on how far you want to challenge yourself. You can either just sort of step through what's here. If you want to make it more of a challenge, maybe keep the R script but blind yourself from the model file, this .txt file, and try to construct that on your own. And we'll go over this in a bit more detail then on Thursday. So let me, before I let you go here, take a breath and see if there's any questions before I send you off. Okay, nothing popping up unless somebody's typing up a long question here, so I guess I'm going to go ahead and escape. I'll maybe leave the question window open for a couple more minutes just to see if something pops up and respond to it if it doesn't. In the meantime, again, questions come up, please make use of the forums on the course website, and I'll keep my eyes posted for those too. Okay, well, farewell. I'll see you again on Thursday.